Okay, it's time to start now. Hello, everyone, and welcome to OBA. Welcome to the 96th free webinar titled PCP Concept, Theory, and Design, presented by our instructor engineer Amr Hilal, who is an experienced artificial lift engineer at Agiba Petroleum Company with 7 years of experience in the oil and gas industry. He holds a Bachelor of Science in Petroleum Engineering and specializes in designing and implementing effective artificial lift solutions like ESP, PCP, and Sakharov. His expertise encompasses oil and gas field operations, including well completion, workover, and production optimization. Before we start, I will make a small presentation about OPA upcoming services and plan. I'm Adel Tahir, and I'll be the moderator of today's session. Uh, we are conducting a wave of live courses. It includes 7 live courses. It started from last November, and it will continue until the end of February. We have already conducted 4 courses with 3 more courses to go. You can scan this QR code to register in the upcoming courses, which is PCB, NMR interpretation, and carbonate reservoir modeling. There is a special discount for our upcoming course, PCB design. Its price is 120, and we have already recorded the ESP course with the price 150. You can get both courses for $180 only and save $90. We have already conducted more than 40 live courses, which is now recorded and available in recording sales in different disciplines like reservoir engineering, G&G, rig and rigless operations, and production technology, and data analytics and safety bundles. You can also scan this QR code to register. Here is our best services, which is mentorship program. It's a one-to-one mentoring sessions by highly experienced mentors. It's like a tailored program based on your needs and based on your request. And your request can include explaining the know-how of a software, practicing on how to produce output results from a software, guiding on personal data, professional guiding for PhD and master. We have already completed more than 45 mentorship program with more than 900 learning hours, and the mentees were from more 8 different countries. You can scan this QR code to register for a mentorship program. Here's a glance of our website, www.opacourses.com, where you can access every service of our services, like watching our recorded courses, enroll in webinars, internship, um, apply for a mentorship, everything you can access through our website. So make sure you pay it a visit. And finally, how to be an OPA ambassador. You have previously seen that we have 2 prices, an original price for the courses and ambassador's price with extra discount. So how to join an OPA ambassador? There are 2 tracks. You can take 1 or more courses with us, or just take a mentorship program. So what will you get? As I've already said, you will get discounts on all courses in the future, and you will get group discounts when you invite your colleagues. Thank you for listening, and now it's time for our session. Engineer Am, the mic is yours.
Hello everyone, good evening. Can you hear me?
Yes, I can hear you well.
Okay, good.
Yeah.
This is Amr Hilal talking to you, and and Jadil, of course, have taken some time to introduce me and introduce OPA courses. For sure, I'm not waiting time for this, but I am starting for our course على طول إن شاء الله. So this is a webinar, a short one on progressive cavity pump. I believe it is short, but I think after that, inshallah, you will have a good hand on PCB theory and design steps. And of course, you will have more data and knowledge if you join our course, inshallah, next week. It will give you a solid background and knowledge on the PCB system, how to design, starting from understanding the theory, how to design the PCB pump, how to troubleshoot the different failures, and so on. So let's start. In this webinar, we will talk firstly about the different artificial lift systems and the different application aspects that we can choose for everyone. Then we can move to the PCB theory and the operating principle. After that, we will take a small presentation on the configuration of the PCB system and different components and parts of the system, starting from the surface equipment, moving to the rod string and to the downhole equipment. After that, we will take a short example on how to design the PCB system, how to choose the best sizing for your PCB, different elastomers, and the selection of different components of the PCB. So most of us know the different artificial lift technologies that we have nowadays. We have, like you see in this photo, the plunger lift, the foam lifting, the gas lifting, the beam pump or the rod lift, the PCB hydraulic lifting like the jet pump, and of course the ESP systems. They are categorized from gas lift is a kind. Then you have the boosted displacement pumps like the rod pumps and the PCB. And moving to the ESP pumps or different centrifugal pumps. And of course, every one of them is characterized by some features, starting from the flow rate capacity for every category, and the net lift that every pump can produce for us. The different characteristics like the withstanding how many temperatures, the different kinds of environments like sand production, gas liquid ratio, and so on. So what do we want from our lift systems in these points? We need the maximum or optimized production, flexibility in production rates, depending on, of course, the decline that we are often seeing in our reservoirs. We need, of course, the lower capital cost and, of course, also the operating cost. We need the least energy consumption. We need minimum environmental impact, and we need the minimum footprint. And this is, of course, mainly direct to offshore applications. In this screen, we can have a very quick look on the different artificial lift equipment that we have. And from your look, you can say that if you are targeting a high production rates, you can go to the ESP system or gas lift system. If you are targeting low production with shallow depths and lower energy consumption, we can go to beam pumping unit and also PCB. If you are targeting viscous oil or low API production with a lot of sand production and gas liquid ratio and considerable gas rate, you can go to the PCB system. If your depths are shallow and your environment is very constrained, like offshore application, we can go to the gas lifting system. For this screen, you can take a quick look and choose the best artificial lift system that best fits your application or your production rate and lift capacity. So how to design or choose the artificial lift system technology application, starting from understanding and predict reservoir potential and establishing the target production levels from the start of the initial production of the reservoir till the end of the reservoir. You can also eliminate the technically infeasible lift technologies. As I told you that if you are offshore, it is different totally from the onshore application. If you are producing sand, it's different from producing sweet oil and so on. And finally, you can evaluate your economics based on the flow rates that you get and the capital cost and operating cost that you deploy on your system or your application. Now, after we have a quick look on the different applications of artificial lift system, we can go directly to the PCP system components. The PCP pumping system, as we all know, it is a positive displacement pump. It is it is considered as a newest method as it appeared in the early 80s. So it depends on, and as we all know, the difference between the common centrifugal pumps and the positive displacement pumps. The centrifugal pumps, it's a theory and the principle depending on delivering a high speed to the fluid that you are pumping, and this speed can be transferred to a pressure through the different configuration of the pump you have. Like for the ESP, you have a diffuser and an impeller. If the speed is high and then it goes through the diffuser, then this speed energy is transferred to pressure energy, and so the fluid can move from downhole to the surface. In the centrifugal pumps, the relationship between the flow rates and the net head or the total dynamic head that the pump can develop is, of course, inversely proportional. So in case of high flow rates, then you don't expect a high total dynamic head and vice versa. In our boosted displacement pumps, like the PCP system that we are discussing today, and also for the beam pumping unit, the positive displacement pumps depends on a chamber or a volume of fluid that is confined in a chamber. And so with the movement of the pump, either it is a reciprocating movement or a rotation movement, this fluid is pumped through the different chambers or the different cavities until going through the tubing till reaching the surface. And of course, it is not highly affected by the differential pressure or the total dynamic head that is applied against the pump. We see that it is literally less affected by this total dynamic head, and it is not like the centrifugal pumps. So you can consider a specific flow rate at different applied back pressure on the pumping system you have. However, in different or highly delta B, you can see the flow rate that it can be affected by the delta B. Sorry. So what is the configuration of our PCB system? Our PCB system is we have downhole equipment and surface equipment, and the thing that transfer the motion from the surface equipment to the downhole pump is the rods, like exactly the same rods that we have in the sucker rod system. So what we have in our PCB configuration, let's start with downhole equipment. As we all know, we have a stator, and this is like a tube, the same like the tubing, but it is covered from inside by elastomers. That is a rubber thing that is bonded to the body of the elastomer to make it easy for the flow and so as not to be affected by the rotation of this rotor inside the stator. So the first thing of the downhole pump is the stator, and this is non-moving part. The second thing is the rotor, and this is the helical rotor that we have. It has a helical shape, and it is the moving part inside the stator. We have the tag bar, and tag bar, this is a small tube, and from its name, we use it for just to know the depth of the rotor or taking our spacing. The non-turn tool, it is a very important thing that is designed to keep the string in a state of to be constant during the movement of the our pump or the rotor itself to keep it constant. Okay, the third thing or the rods we have from the rotor to the sucker rods or the rods that we have for delivering the energy. We have pony rod, and then the sucker rods. We have something called the shear coupling. The shear coupling is used if we have, for any reason, the pump stuck for any reason. We can release our string from this shear coupling, depending on shear pins that we have, and designed pre-designed torque or even tension to release our system from this downhole pump. Of course, we have two types of PCB. One of them is a tubular one. In this case, the stator is attached directly to the tubing itself. And in this case, we have different capabilities of the stator to be with different sizes to fit inside our casing. The other kind of the downhole equipment is the insertable ones. The insertable ones is totally deployed inside the tubing through a pump seating nipple that we have a profile to sit inside our pump. And in this case, we are limited by the inner diameter of the tubing. And of course, we can say that it is designed for lower flow rates than the tubular ones. Okay, and now let's move to the surface equipment. The surface equipment, of course, we should have the drive head. This drive head is the thing that drive the rods itself in a rotation and then to the rotor itself. So this is the drive head or surface drive. Okay, how can this drive head take its rotation from the prime mover? The prime mover is the electric motor or even a gas or diesel motor. And of course, we can generally say that it is a prime mover, not just an electric motor. Okay, so the prime mover emits the energy or is responsible for our energy. Then this energy or rotation is transferred to the drive head through a sheave and belts to transfer the torque and power to our drive head. In this red thing, inside it, there are the sheaves and the belts. So we have talking about now about three components: the prime mover, the sheaves and the belts, the drive head. The fourth thing is the polished rod itself, like the one we use in sucker rod pump, and the rod clamp that keeps the polished rod in place. after that, we have the stuffing box. And what is the importance of the stuffing box? The stuffing box is the same, keeps our flow or our fluids inside the tubing and to the pumping tree, so as not to affect the drive head or other surface equipments. So it is protecting the surface equipment. Okay. Now we have no news that the PCP is used for heavy oil application. Okay, let's say that now around 70% of the applications of the PCP is deployed for the heavy oil systems. The other 15% is for coal bed methane, and medium oil is 12%, and a small percentage is used for light oil and water source well. So our basic percentage for using the application of the PCB is for heavy oil or viscous oil. This is a very important thing to talk about the PCB. Now we knew that a PCB is its operating cost and capital cost is nothing compared to the surface or the beam pump itself, and nothing compared to the ESP. Of course, its application is very simple and its theory is very simple. However, we call it as the least forgiving artificial lift method. What does it mean, the least forgiving artificial lift method? As we have talking before, we have said that the stator have something inside that is called the elastomers. The elastomer is the rubber element. This elastomer should be selected very precisely and should be taken into consideration very, very, very importantly during the design of the PCB, because it is highly affected by very high temperatures, of course, and aromatic content of the fluid that you produce. If the fluid that you produce has a high gas rate, and in this gas there is aromatic components. The aromatic components mean the rings that we have in benzene, what we call it benzene compound. This highly affects the elastomer, our elastomer, and يعني causes it to be brittle with time, and so to be broken. And after that, the efficiency of the pump is not very good, or it is very bad to produce the fluids that we are targeting. So if your PCB is matching the application that you designed it for, it will be the very beautiful artificial lift system that you use. If there is a small or bad design for any of the parts of the PCBs, including the rotor or the stator or the elastomer itself, or the spacing you make during the PCB design, you can have a strong failure in your system that will require a workover. يعني in this case, you can work over the well to recover or retrieve the tubing and of course the tubular stator inside it. And we can eliminate this, of course, by using insertable pumps. It will just need a pulling unit to retrieve our PCB and then reinstall it again. So that's why we are calling the PCB the least forgiving artificial lift method. So what are you telling me about the best applications of PCB or the different ranges for the ESP that you recommend to use? And let's have a quick look on this table. The typical range for operating depths from 600 feet to 4,500 feet. For the volume, we can say that we can produce up to 2,500 barrels per day. And in some cases, with a special equipment, we can reach 6,000 barrels per day in different applications. The operating temperature, the recommended one maximum is 140 degrees Fahrenheit. However, we have some special equipment to produce at temperatures like 302 degrees Fahrenheit. The wellbore deviation, or in this case, our dogleg severity, can withstand up to 6 degrees per 100 feet. It is very good in corrosion, very good in gas handling, and it is excellent in solids handling. The recommended API gravity for the oil that you produce, it can withstand starting from 8 degrees to 45 degrees. However, its best application is below 18 degrees API. The prime mover, as we talked before, can be electrically driven or using diesel or gas. Offshore application, of course, it can be good in offshore application because it has a limited space that offshore applications can constrain us in this design. The system efficiency is 55% to 75%. And these are the typical applications for the PCB that we recommend our users to use PCB for. I will take a minute here just to ask you if something went good, or you can get what I'm talking about, or anyone have any comment before moving to other parts. So just tell me in the comments or even by your voice if everything is good now, or you need to ask about anything.
Can I ask a question?
Yes, you can ask a
Hello.
question.
Hi, my name is Ryan Cadeno. I'm a petroleum engineer. And my question is more related to what you will be discussing further in the webinar. Will we be touching on anything related to PCP design? And what software do you recommend for PCP design? That's it.
Okay, thank you. Any other question?
Hello? Hello?
خلاص, okay, let's continue our
Question from Engineer Ahmed Obaid.
Hello, my name is Ahmed Obaid. I am a field operator in the CNBC in Hadida field.
okay.
I ask you about this PCB pump. Can this
Yes.
PCB pump, this application, this connected for crude oil, heavy crude oil? Because this
Heavy.
crude oil is heavy and light.
Okay.
I ask what is the connected this oil in the heavy oil and the medium oil.
Okay, okay. Thank you. I will answer.
Okay, thank you.
So for our first question, our engineer asked us about the design of the PCB and the best software that we are using in the design of the PCB. We will have a small capture of our PCB design in this webinar, and of course you can have more detailed PCB design in our next course, inshallah, that is starting next week. But today, inshallah, I believe you can have a strong background and hands-on PCB design. However, the design software that is currently now on market is called the CFIR. You can search about it, and I will talk about it later on our course, inshallah. It's called the CFIR. It is a software designed mainly for designing the progressive cavity pumps. Sorry, for the second question, our Engineer Ahmed asked us what is the best application for the PCB, and of course we have said that more than one time. It is recommended for producing the heavy oils that is lower than 18 degrees API. This is the best design or the best application for the PCB, because this viscous oil, as we all will know right now, the viscosity of this fluid increases the efficiency of the pumping system, especially in the positive displacement pumps, not like the centrifugal pumps. So the best application, again, is below 18 degrees API. However, this PCB can work up to 45 APIs in special conditions. The special conditions because we can different effects can combine together during your PCB operation, like sand production, high gas oil ratio, light oil, and in this case you cannot tell me that the PCB can work in these conditions. It will be very hard. So you can dedicate your PCB or the best size that you use for a special application, and we can dedicate this PCB for your application. So we are telling you that the PCB design is case by case. You can have a look on your application, specify the different challenges in your application, and then decide if your PCB is the best artificial lift application for this design, or any other lift can help better than the PCB. So let's now move to the next slide. The operating envelope or the PCB system. Of course, the operating envelope is it means that the flow rates that the PCB can produce, the net lift that it can deliver, or the total dynamic head that it can deliver. And of course, these are limited by the temperature effects, the sand content or sand production, the gas liquid ratio, and many other factors. But the main two factors in the operating envelope of the PCB that your design is based on is the flow rate that you are targeting and the net lift or total dynamic head that you require. And this graph can show you how to choose or decide your best PCB. This curve is the same like centrifugal pumps. In this curve, you can see that the total dynamic head or the net lift the PCB can deliver is inversely proportional to the volumetric capacity of the pump. And of course, it is constrained by the size of casing itself. The size of casing decide what size of the stator you can use, because if you are running a smaller casing, you cannot run a big pump inside. And of course, if your casing is getting larger, you can run a tubular PCB or stator attached to your tubes that is bigger and can deliver higher flow rates and a higher net lift you need. So these are the common PCBs that is right now in the market, decided by the flow rates and the net lift capacity. These figures of the stator or the configuration of the stator with the rotor itself. Of course, we have different shapes of the stator and rotor itself. We will know يعني specifically or in more details about these configurations in our course, inshallah, because we have now a limited time to talk about these rods and stators configuration. We need a lot of time to talk about, and it will highly affect your application or your PCB design. The shape of the rotor itself, the pitch, the diameter, the elastomer material, the stator pitch, and many other factors. So after that, what is the PCB system advantages after we have talked about the lower energy consumption? First of all, the lower energy consumption than many other artificial lift systems. Second thing is the ability to produce highly viscous fluids. The third thing is it can produce highly sand content. The fourth thing is it can produce high gas oil ratio or high gas rates with a minor slippage, rather than for example, the Saccharode pump or the ESP pumps. The fifth thing is the low capital cost and low operating cost. Of course, the capital cost is high, but it is lower compared to the other artificial lift system like Saccharode pump or beam pump and the ESP itself. These are shortly the advantage of our PCB system, and that's why many companies are now deploying it for different application in their fields to take this advantage from the PCB systems. And of course, there are concerns and different challenges during the running of the PCB, sorry, we have talking about, and we have said that it is the least forgiving method of artificial lifting because of that. One of them is the incompatibility between the elastomer or bonding system inside the fluid or aggressive fluid that you are producing. One of them is the limited diameter of the stator and the limited capacity inside the casing you have. One of them is the fluid level that you have or the high decline in your reservoir that makes the fluid level above the pump is very low, and so it takes something called pump off condition that raise a very high temperature inside your pump, and so affected the elastomer and can burn it, and can burn also the bonding material between the elastomer and the body of the stator itself. The wearing that can happen between the tubing and the rod string, and it is very common in the pumps like the PCB and also in the Saccharode pump, because we have a friction by nature happens already inside the tubing between the rods itself because of this reciprocating motion or this rotation motion, and this can affect the tubing, of course, and it can cause many tubing leaks with time. So these are the main concerns about the PCB or the issues that it raises if the current fluid conditions or the conditions of the environment or your well cannot meet the PCB system. We have talking, of course, about the advantage of the PCB over the Saccharode and even over the ESP system, and the best typical applications for the PCB. And to save more time, let's talk about the components of the PCB shortly. This is a drive head, and its components are 4, and every one takes a very important function, starting from the stuffing box, the braking mechanism, and the sheaves and the belts, and the thrust bearing that it takes the axial load of the rods itself, because this drive head can withstand the axial loads or the loads of the rods itself and the pump, of course, during the operation. This is the drive head. Second thing is the prime mover, and it can be electric or gas or diesel prime mover. The advantage of the gas or diesel mover over the electric motor is that it can be running with different speeds, and so you can run your PCB with different speed without the need for the sheaves or belts. But in case you are using the electric motor, you are limited by the frequencies that you have inside your area. And so, of course, if your motor is running with a fixed speed, like for example, 1000 RPM, you need, in this case, sheaves and belts to transfer this motion and reduce this RPM to the best motion or the best RPM that is fit your application and depending on the flow rates you need. The motor controller or the VSD, this is the switchboard or even a variable speed drive you use to run your motor with a lot of, let's say, automation on site and setting points. You can put setting points for every parameter like torque and RPM and different parameters inside your system using these variable speed drive and your switchboard. Of course, we know that the switchboard is limited in its features to like on and off start panel and some minor automation systems that like the auto restart option. But of course, if you are using a variable speed drive or variable frequency drive, you can deploy it on your system, taking a lot of advantage. And this is, of course, for all the artificial lift method, not just for the PCB system. The other components in the surface equipment of the PCB is a stuffing box, and you have talked a lot about the stuffing box and its importance in our PCB application. The pumping T, of course, you need a pumping T below your drive head that is responsible for diverting the fluid that's coming from below towards the flow line you have with a sealing element so as not affect the surface equipment that you have on site. We can also deploy a rod POB with the pumping T inside one block. In this case, the rod POB takes advantage on seizing on the polished rod during any action you need to apply on your surface equipment, like changing the sheaves or removing the drive head or any other stuff. The polished rod itself is driving or transferring the movement from the drive head towards the rods below and, of course, towards the downhole pump. The sucker rod string, this is the transition state between the surface equipment and the downhole equipment. It is responsible for transferring the torque and motion from the drive head and polished rod towards the downhole equipment, especially the rotor itself. And of course, they are affected by many stresses. And to highlight them, the first one of them is the torsional stress, because as you know, we are rotating our rods, so it can be affected by the torsional stress that can affect them to make it can shear roads if it designed badly or not taken into consideration during our design. of course, because of the length of the rods, it is also affected by the high tension, especially on the most upper parts of the rods themselves, because they are opposed to the weight of the rods themselves, and so we call it axial loads. So to make a summary for the rods, we have two main stresses affecting the rods: the torsional stress and the axial stress. The downhole pump itself, its components are mainly the rotor, that is the moving part, and the stator, that is the stationary part. And of course, we have talked about this. This black dark thing is the elastomer. You can differentiate it between the stator body itself and this elastomer, that is the dark thing that is bonded very strongly to the stator itself. And this material is mainly based of rubber or different kinds of polymers, and for different kinds of applications that can withstand different temperatures and different components or composition of the fluids that you are producing. And now we have come to last thing in our session or our webinar, that is the main part of our webinar. It is the PCB design and sizing methodology. We will have a very, very short but is very focused one to design our PCB and take a decision of which pump or the best one that fits your application. So let's take an example. This is a given data about a well. A well data, casing size is 5.5, 5.5 inch, tubing 2.7/8. The rods are 7/8. The perfs are at 3,550 feet. The pump setting depth is 3,600 feet. Bottom hole temperature is 86 Fahrenheit. The fluid data, oil gravity is 20 API. Water specific gravity 1.12. Water gradient for this fresh water is 0.43. The gas specific gravity is 0.7. The oil viscosity 1 centipoise. The production data, you are targeting a rate of 644 barrels per day. Water cut 75%. The fluid level is 3,500 feet. And you can say that this fluid level is very low, which means that your reservoir is declining rapidly and you don't have a good pump submergence for this application. And of course, you will need a net lift, a very high net lift in this application. The tubing pressure or the flow line pressure is 55 psi. The casing pressure is 60 psi. The design parameters. Let's assume that the maximum RPM that you can get from your drive head on your motor is 400 RPMs. Maximum pressure loading is 90%. Pump efficiency is 80%. The drive head efficiency is 95%. The belt and sheaves efficiency is 97%. And the power cost is $0.1 per kilowatt. So we will start designing this well, starting from the design, the displacement or the pump that fits your displacement or flow rate capacity. This is the first thing. The second thing is to choose a pump that fits your net lift capacity or the discharge pressure and the difference in pressure between the discharge and the intake pressure to fit this application. The third thing is to choose the best rods that can withstand the torque applied on this rods and for this application, and then transfer to the surface equipment, choosing the best motor, the best drive head, and then calculating the energy consumption and this energy consumption cost that you can get from your PCB. Okay, let's start with the pressure profile. The pressure profile, as you can see, this is the curve that representing the well itself. We are installing a pump at this depth. So from the pump intake pressure, our pump will raise the pressure from this to this discharge pressure to be able to flow slowly and flow precisely to the tubing head pressure. This is a small chart or a figure that represents your installation, and you can understand from it how your PCB can produce or can operate in these conditions. The first thing is how to calculate the net lift capacity. The net lift capacity is a different, very basically and very easy. The net lift capacity is the difference between the discharge pressure and the intake pressure. So the intake pressure equals what? The intake pressure equals the casing head pressure plus the hydrostatic column that the gas is presenting between the casing head and to the fluid level, and then the liquid head or hydrostatic head above the pump. This is the intake pressure. The discharge pressure represents the pump tubing head pressure plus the hydrostatic column above the pump inside the tubing, and of course the friction losses that is applied inside the tubing during production. Okay, let's calculate it quickly. From the figure you have, we have casing head pressure as we have seen from the given data. The casing head pressure is 60 psi, and for the gas gravity, the hydrostatic column till 3,500 feet, it represents around 1 psi. Then the fluid level, depending on water cut 75% and oil cut 25%, you can get an average density for this mixture, and then from it you can calculate this column how the hydrostatic head be like. So from our calculations, the hydrostatic head from 3,500 feet till the pump depth, it is around 40 psi. So the total pump intake pressure around 101 psi. The casing head pressure. The casing head, the pump discharge pressure. Pump tubing head pressure is 55 psi, as we have seen from the given data. The percentage of the oil, the 25% from the specific gravity of the oil, you can get the hydrostatic column that this oil represent. And also for the portion of the water, you can calculate the hydrostatic column of the water. And of course, we are dealing in this example with a mixture of fluids that you cannot produce oil alone or water alone. This is a mixture that you are producing. So you are supposedly to calculate the density of the fluid you are producing together and take an average number or average figure for this mixture for the specific gravity, and then calculate this hydrostatic column, how much weight that is applying inside our pump. Then after that, you have now two parameters, the tubing head pressure and the hydrostatic head. The third parameter is the friction loss. The friction losses, it can be in many cases, they can be negligible, but to be precise, we can calculate our flow losses or friction losses, of course, depending on Reynolds number. And we all know, I don't know if someone doesn't know about Reynolds number. It is a very important equation in our fluid mechanics. So the Reynolds number, we use it to determine the friction factor, and from it we can calculate from this equation. From this equation, we can calculate the Reynolds number, and going is a chart of Moody chart. We call it Moody chart to calculate the friction factor, and then apply the equation of Reynolds to calculate the pressure losses inside the tubing, depending on this kind of flow. Either it is laminar flow or turbulent flow or transient flow. From different kinds of this flow, we can get our flow equation to calculate the friction losses inside our system. And of course, we will take much more slides about this in our course, inshallah, because we have limited time here to talk about. But this is a very basic knowledge about how to calculating the friction losses inside the tubing. After that, after you have got the discharge pressure and the intake pressure, you can subtracting each from each other to take the delta B. And of course, to design your PCB, you cannot depend on this delta B. We have to take about something called the load factor or maximum allowable load, that it is default 85%, to take into consideration something maybe may happen during your operation. So if you need actually a net lift X, for example, you should divide this X by the C, or the maximum allowable load, to get the minimum lift capacity of your PCB. In our case, we have got the differential pressure between the pump discharge and the intake pressure. In our case, it is 1,637 PSIs, and dividing it by 90%, we can get 1,818 PSIs. This is the minimum net lift that you require from your PCB. So this is calculated in PSIs. Can you convert it? Because almost designation of the PCB system is designed on the net lift in feet or in meters of fresh water. So to convert this PSIs to how many feet of fresh water that the pump can lift, we can divide this number by 0.433. This is the density or the specific gravity of the fresh water to get the net lift from your system. The second thing, in this case, I forgot to tell you, in this case, it will make around 4,100 feet of fresh water. The second thing after designing the net lift capacity is the displacement capacity. So what is the minimum requirements of the displacement of this pump? We have shown in the given data that we have target production around 644 barrels per day. So what is the minimum lift required from the pump? We should, of course, this Q total that we required, divide it by the efficiency of the pump. It was given also on the example, and divided by the design RPM that you have, to give you the minimum flow rate that you have in this unit, cubic meters per day per RPM, or even barrels per day per RPM. This is the unit designation for your system. So let's calculate it. Divide 644 by 400 RPM. That is the operating or the target or the desired RPM that you require to work on. 400 and multiplied in the denominator by 80% efficiency of the pump. It was given. This number also was given in the given data. So after that, this gives you the minimum capacity of the pump that you require. It can give us around what? Around 200 barrels per day. This gives us around, the pump displacement gives us 200 barrels per day. So now we have decided the minimum lift requirements or net lift head required by our pump, and required also the minimum flow rate that the pump can handle or our pump is designed for. So in this case, we have a charts and many charts for many manufacturers. We have for the PCB systems, many manufacturers, and each one of them has a lot of charts and tables for every pump that gives you the flow rate capacity of the pump, and gives you also the net lift capacity of the pump, and many features for the rotor, stator, elastomer, and many other components of the system. So all what you need is to go to the tables that your manufacturer or your contractor have, and in this case, you choose from these standard pumps that they have the best one that fits your application. You now know the minimum lift requirements and the minimum required capacity from your pump, and then you should decide. You choose a one similar to the requirements if it appears or if it is existing, or even choose a higher one, not a lower one, because the higher one will give you exactly what you want, but the lower one cannot give you exactly what you want. So in your decision, you should choose a pump that meets or exceed the requirements of your application. From this table, we see the pump highlighted here, and we'll talk more about the designation of the PCP pumps later on, inshallah, about what is the designation or codes for the pumps itself. This imperial designation for this pump, 200-4100 feet. This means that this pump can produce 200 barrels per day per 100 RPM. If it running at 100 RPM with zero net left or zero differential pressure, it can give you 200 barrels per day. 4,100 feet, it can work till differential pressure reaching 4,100 feet. So from our application or the design, we can choose this pump and it can be suited to our application. So we have now gone to choosing the pump. We have chosen our pump that can give us the requirements of the system. Now we need to move to the other parts of the system. We have chosen the pump. Then how can you choose the rods? The rods itself. The rods, of course, are affected by many parameters like torque, stress, and axial loads. So you should choose a rod. And he has told us in the given data that the rods we will use is 7/8 rods, that its grade is MD or D category. So let's have a look on the yield strength of the system and the torque that the system can withstand. These are the specs of the rods that we are using. So we should check now if these rods are exceeding our requirements or it cannot fit our requirements. So we need to calculate the torque that we have in our system, and we need to calculate also the effective stress by combining the axial loads and torque stress together in one equation to get the effective stress and comparing it to the yield strength that this rod can withstand, and then decide if this rod fits your application or not. Also, the torque requirements, calculating the torque, the hydraulic torque and the friction torque. We will have it in the course because we have limited time. But as an example, the effective stress is a square root of C1L square in all this equation that combines the torque load and the axial loads, and also taking into consideration the minor and the major diameter of the rotor that we are applying. So after you calculating the effective stress, you can compare it to the yield stress or yield strength of the rod. And if our calculated stress is lower than this yield strength, so our rods can fit this application. So we have now chosen the pump and the rods. What is remaining? The surface equipment. So we need to calculate or choose surface equipment that fits our application. This is a term called the Elton life. Elton life, this is a very common idiom used in our designation for the drive head. That means the run life of this system until 10% of the interior components are damaged or not working with the same efficiencies that you require. This term is called L10 life. It can use it for calculating the run life for this of this drive head, and this equation that represent it depending on many other parameters like the polished rod axial load that it withstand below it, and the polished rod speed or running rotation per minute that the polished rod are running with, and the thrust bearing dynamic load rating. This is the dynamic rating for the drive head that it can withstand. So if you are, for example, from our application, if you are using the category 150K, this drive head, and we can from this equation and from the tables, we can see the thrust bearing dynamic load that is rated for, and then calculate how many years or how many days or how many months that this drive head can withstand before a 10% of its interior components have minor or major damage. After that, we need to choose a prime mover or polished rod. For the polished rod horsepower, this equation can calculate our polished rod horsepower depending on the RPM that is running with and the torque load that it was stand. We can also choose this motor, the 40 horsepower motor, depending on force of the horsepower required from the polished rod. We can choose the horsepower required from the motor, and we should take into consideration that this power of the motor is transferred to the drive head and to the polished rod. So there is a mechanical deficiency in the system. You should consider it during your design. Of course, you have a motor efficiency and a motor power factor, so these parameters also can be taken into your design to have a quick look on it before choosing the suitable motor for your system. And to make it easy for all of us, there are standards of motors that our manufacturers have. They are different in ratings of the horsepower and torque and so on. So it will be easy for you to choose a little bit higher one or a much higher one that fits your application. And in many cases, or in most cases, I'd say in most cases, the motor requirements and the drive head requirements are fitting the application that we are requiring. Okay, so after choosing the downhole pump and then design for the rotor, then choosing the drive head, choosing the polished rod, choosing the motor. We have now chosen everything. So let's calculate now the energy cost that we have from the system. The energy cost that costs us from this system. Let's calculate first the ampere. To calculate the kilowatts, let's calculate the ampere. Of course, you are running with a specific horsepower. If you divide this horsepower by the voltage and taking into consideration the factors or this coefficient in your equation, you can calculate the ampere or the current required from the system. And by multiplying the ampere times the voltage, you can get the kilowatt or power required from the system. And from the given data, you have been given the cost per kilowatt. After that, if you know the kilowatts that you have or need from your system, you can calculate the power cost that is required for running your system. The final slide that we have, or the final thing to end with, is the system efficiency. The system efficiency, we have an overall system efficiency and an overall mechanical efficiency. The mechanical efficiency of the system, or the overall system efficiency is got by multiplying the pump efficiency or the pump torque efficiency times the rod string efficiency times the drive head efficiency times belts efficiency times motor efficiency. You can get it all from the given data. We have been given all data from the given data slide. And to calculate the overall system efficiency, you can multiply the pump efficiency by the overall system efficiency that you have calculated just before. Now you can get overall system efficiency of your system. That is يعني an example of how to choose or design the PCB that best fits your application by calculating the net lift capacity and the required displacement capacity from your pump, and ended by calculating the horsepower required by the system and the overall system efficiency you got from this PCB that you have chosen. Of course, we have much more examples and much more details for these examples on how to calculate each parameter and each variable of these variables inside our system. We will have, of course, time to talk about it later, inshallah, in many other sessions and in our course, of course, to talk about it so as to يعني get a strong and solid background on the PCB design for all of us, inshallah. This is the end of today's session. Thank you all. And I am totally free to answer any of the questions you have. For everyone, if you have a question, please ask, يعني open your mic and ask it. You are totally free to do that.
Thank you, Engineer Amr, for this fruitful webinar. Let's have a 2 minutes break to fill in the feedback form that I will send in the chat box right now, and then we will be able to receive all your questions.
Okay, take your time.
Okay, attendees, you have 2 minutes to fill this feedback form and start asking your question on the chat box, or if you want to open the mic and talk, it's okay. I will let you unmute yourself now. So you can unmute yourself and ask any questions you want. Okay, we already had two questions during the webinar from Engineer Ahmed Obeid. He was asking what are the problems of damage in the down the well during oil production. This I really can't understand your question, Engineer Ahmed. If you If you can open the mic and ask your question, it will be very great. So we have another question, Engineer from Engineer Muhammad. What are the latest technology of PCB, and what are the most challenges of using PCB with unconventional wells with light oil and high GOR? Engineer Muhammad, can you hear me well?
Okay, I can hear you. Please repeat the question.
What are the latest technology of PCB? This is the first question. The second question from Engineer Muhammad, he was asking what are the most challenges of using PCB with unconventional wells with light oil and high GOR?
Okay, let's answer the first question. What are the latest technologies of PCB? Of course, as we have said during our seminar, the PCB is very recommended in the heavy oil or viscous oil, and it gives you the best efficiency in this application. What happens, or what is these latest technologies to overcome the challenges that you face in the light oil application? First of them is we are currently working on a lot of elastomer components that can fit aromatic content in the light oil, and can also overcome the problems that you have from the overheating of the low fluid level that you face in different application. So the first thing is deploying different elastomer by applying the autoclave compatibility test for different many kinds of elastomers, and even يعني metal to metal seal يعني using the rotor and the stator without any elastomer, so as not to affected by this aromatic content or the very high temperatures coming from this application. So the latest technologies are using different elastomers, using different kinds of, or combining two kinds of VCP. One of them is the charge pump, and the other one is the main pump or main producer pump. The charge pump is responsible for handling the higher amounts of the sand content and the gas content to make them all together inside a flow and increase the speed of this fluid. So for it to come to the main producer pump, one fluid that you can get alone inside your pump. One more thing is that you have different gas separators for the PCB system, and of course deploying the VSD system with your PCB and remote controlling for your PCB can give you a lot of advantages. And of course, if you are giving your system some setting points to work and pump off during some conditions, it can give you a very good remote surveillance for your system, so it can withstand the higher torques that's coming, or even the overheating, or even the low fluid levels that the pump is facing. So that is your first questions. The second question, someone was asking about the challenges that we have from the PCB. Please correct me, Adil, if you remember.
In unconventional wells.
In unconventional wells, like, for example, let's say a very high deviated one, or even, for example, a fractured or a high pressure, high temperature wells, or even wells with thermal stimulation, for example. As I told you, the factor that is يعني constraining us or limiting our design is elastomer and the bonding between the elastomer and the stator. These are very important factors during choosing of your PCB. Maybe your elastomer can withstand a temperature of 300 degree Fahrenheit. 300 degree Fahrenheit. This is your elastomer. You can say that our PCB can work in this condition, okay? But the bonding material between the elastomer and the body of the stator itself will withstand only 250 degrees Fahrenheit. So what is the working temperature for your application? Of course, it will be 250, not 300. So you should choose correctly or design correctly the best elastomer and bonding material for the temperatures that you have. Another example, if you are running your PCB in a very deviated well or a well with a higher dogleg severity, what consideration you should have? As we all know, this rotational motion can make a fatigue stress on the body of the rods themselves, or even can make fatigue stresses on the tubing and make cracks with time. So you can deploy many guides on the rods or the deviated section, or even the highly dogleg severity section. You can deploy molded rod guides on your rods, and you can get benefit from them. You can also install something called tubing rotator that it makes 2 rounds per day, to distribute the loads on the different sections of the tubing or different sides of the tubing during the day, so as to eliminate this high severe effect of the friction between the rods and the tubing. So this are examples of the challenge that you can face during running in your PCBs in unconventional ones.
Yeah. We have another question from Fidan Siromova. He didn't understand the graph. I think the first graph of the presentation. The
I
one
think
with the 3 curves.
I think he means this graph. This one. Yes, please correct me.
This one, the one,
Yes.
the previous one.
Which one?
Earlier, more.
This one? Yes, this one?
Yes, this one.
Okay, this is a very simple graph that representing the relation between the net lift or the dynamic head and the flow rate. If you have dealt with the ESP systems before, you have taken a graph like this. It's an inversely proportional graph that representing the relationship between the fluid rate that your system can deliver and the net lift that it can withstand. It is an inversely proportional relationship. If you require from the system very high pressure, of course, this system cannot get you this maximum flow rate. You cannot combine a very high flow rate with a very high differential pressure, because the systems can work in either conditions. You can get a very high flow rate, of course, but the total dynamic head that you get from the system, it will be low, because of this inversely proportional relationship. Because something we will have later in the course, it will explain the relationship between the flow rate and differential pressure in terms of something called slippage. The slippage that we will talk about later, the slippage represents the percentage of the flow rate that cannot be delivered from a chamber to chamber because of the high differential pressure. So you are losing some of the flow rate you have during the production because of this high differential pressure you have. That's why we are calling this relationship between between the flow rate and the net lift is inversely proportional relationship. And of course, the blue dashed lines, they are representing the limitation of each size of casing. So for example, for the 4-half casing, they are limited by all the points below. The 5-half, they are limited by all the points below. For the 7 inches, they are limited by all the points below. Yes, I think now it's clear.
Thank you. We have a question from Engineer Abdullah Mustafa. He was asking if we have some real-time monitoring and troubleshooting examples in the course.
If we have real-time
Real-time monitoring and troubleshooting examples in the main course.
yes, we have. Inshallah.
Okay, great. So we
will talk in the course, of course, يعني a dedicated section for the different kinds of the concerns that we face in the PCB design. For example, the sand control, the sand content production, the gas production, how we can troubleshoot, how we can operate, and how can we choose the best rotor stator configuration to fit this application even before deploying the system in your well.
Okay, we have 3 more questions from one from Engineer Manuel. He was asking what is the difference between sorry. The ESPCB is still a PCB and where is recommended to use it?
This is a very sneaky question. The ESPCB is a combination between the PCB and the ESP. It resembles the PCB in the stages because the stages are PCB stages. You have rotor inside that's running by a motor and a cable deployed that is resembling the ESP. But of course, finally, we have stages, not an normal impeller and diffuser in the stages of the ESP, but you have a stator and a rotor inside the ESPCB. So you can handle much more sand content, much more gas rate, but you are deploying a cable to the system and you are running a motor from below, not from the surface equipment that we have in the PCB. So it is a combination of the ESPCB that combines both the good things from both artificial lift systems.
Okay, thank you. We have a question. How can we troubleshoot if PCB is tripped on high torque setting reset? Can you explain it?
Now, I think this question is advanced one we can talk about later in the course, and I think this webinar is limited to the intro about the PCB theory and design. I think it is not suitable to answer this question in this webinar, but of course we can answer, but let's postpone it to the course. يعني.
Okay. The last question, I believe, from Engineer Ahmed. In the operation, PCB will shut down due to equipment down. I can't understand, Engineer Ahmed. Please open the mic if you can. Engineer Ahmed Obaid, you can unmute yourself now and start asking your question in the mic. Until then, let's have a question from iPhone. What is the effect of casing pressure upon pump intake for the PCB?
The casing pressure, of course, the pump intake is we can the pump intake is an equation combining the casing pressure plus the column above the pump. So the casing pressure is one of the major points on the pump intake. It's a very simple equation, I think. The summation of all the pressures above the intake point is representing the intake pressure. So the casing pressure is one of them, of course.
Okay, thank you, Engineer Am. I think this is all for today. Thank you again, and thank you all the attendees for attending this webinar. Also, there's a kind reminder that we will be launching a PCP live course on next Saturday. So make sure you check the content. I will send a link in the chat box right now with the content link and the registration link. So thank you and see you soon, inshallah, in our next webinars.
Thank you, everyone. We are waiting for you in the course, inshallah, and we are pleased to meet you now. Thank you.